Greetings, AP Chem. Today we are going to be talking about solution making. So last time we talked about how a solution kind of forms and what to expect with the molecules and particles within the solution, as well as talking about calculating concentration. And today we're going to take that another step further by talking about actually physically going into the lab and making a solution. So in theory, we'd be doing a lab and all that kind of stuff, but we're just going to have to kind of talk about it right now, which is unfortunate, but part of the deal. So when you make a solution, the expectation for the College Board is that you're going to be expected to know how to make the solution in terms of both the math to give the proper quantities of things you need to actually make the solution, as well as the technique for making a solution from both a solid, so like pure chemical, or from a pre-existing solution that already exists. And so we're going to kind of go over both of those today to make sure that you know how to do them, including the math and the technique. And it's going to require some specialized equipment that you maybe have used and maybe haven't used, depending on how much experience you have with this particular stuff. So I'm going to talk to you guys about the specific types of glassware that you're going to need, and then we'll talk about the math behind it. So when we talk about glassware, there are kind of two kinds of glassware that you are going to run into. One of them is graduated glassware, and the other is volumetric glassware. And we're going to talk about graduated glassware first, and then we'll talk about volumetric. So graduated glassware is glassware that can measure out several different volumes of liquid. So it has different graduations marked on the side of the glassware. Now, the kind of least useful for us is going to be a beaker. And I basically don't ever use a beaker unless I am either using it to contain a chemical reaction or I need to dissolve something in water and the amount of water is not super precise in terms of its requirements. Otherwise, a beaker is just there to contain a chemical reaction. You are not going to use a beaker, just flat out not going to use a beaker to measure out anything with any kind of precision, because the graduations on the glassware are so wide and it's just not super useful. Now, a more useful piece of equipment is going to be a graduated cylinder, and you can use those to measure out exact volumes. Graduations on a graduated cylinder typically go anywhere from 1 milliliter per line. And if you're using a 10 milliliter graduated cylinder, they can get down to either every 0.2 milliliters. And I don't think I've seen a 0.1 milliliter breakdown on a graduated cylinder. You can use them, but if possible, you are going to want to use either a pipette or a burette to dispense the exact volume. Now, a burette is a glassware piece that we're going to be using specifically for titrations, but in a pinch, you can use it to deliver a specific amount of liquid. And when we get into titrations, we will talk a little bit more about burettes, but pipettes are the big thing we're going to be using. When you take a look at a pipette, this is just one example that you guys are seeing here. It's called a serological pipette, and they are even different depending on the type of pipette you have. So this pipette here has graduations. It's technically a quote unquote 10 milliliter pipette. Even though if you look at it, each of these major hash marks here is 1 milliliter. And if you count the hash marks, it actually goes up to 11 milliliters, but it's considered a 10 milliliter pipette. And if you notice, there's no mark here at the bottom for the actual 10 milliliter line. So what happens with this pipette is that the last milliliter is kind of assumed to be this bottom part here. And when we talk about a pipette, you can use them in kind of two different ways. You can either use the pipette to measure out the volume and just pull in as much liquid as you need. You'd use a pipette filler, which is like a little roller on top, and I'll show you that when we get into our lab. And let's say you need 3 milliliters of, or in this case, 3.2 milliliters of a liquid. What you would do is you would do 1, 2, 3 milliliters pulled in, so up to the 7 line, and then an additional 0.2 milliliters pulled in, and then you'd release it out, okay? You can also approach it from looking at letting out a certain amount. So with this first pipette here, what we do is we pull in just as much liquid as we need, and then let it out into whatever reaction container we're going to be using. In the other approach, what you could do is you could fill it up to the 0 line with whatever liquid you're trying to suck up in the pipette, and then you could let out 3.2 milliliters, and so you'd actually empty it down to the 3.2 line. So when you read a pipette, it kind of depends on the approach that you are actually personally using when it comes to using the pipette. So for instance, if I ask you to read this pipette here, okay, if we read the pipette, it tells us technically, if we look at the meniscus here, that we are at 4.5 milliliters. But depending on how you're using the pipette, it's going to give you a different volume of liquid. If I let out liquid from the 0 line down to this here, I would have let out 4.5 milliliters. However, if I pulled in liquid in this pipette and pulled it up to here, I would have pulled in 5.5 milliliters. So it's really important with how you use the pipette as to how you're going to read the pipette. And just like when we use a graduated cylinder, you want to look at the meniscus, and then you're going to look at the bottom of the meniscus, not the top. The meniscus is actually caused by attractive forces between the glass and the intermolecular forces within your substance. So the water kind of is attracted to the glass and it creeps up the side. Okay. Another type of glassware that you are going to encounter is going to be something called volumetric glassware. Now, volumetric glassware is not graduated, so there aren't multiple volumes that you can actually use. They only contain one specific volume of liquid. So you'll hear it either be a 200 milliliter volumetric flask or a 10 milliliter volumetric pipette. But what happens is that volumetric glassware, because it only contains one volume, has to be really precise, otherwise it's useless. So if we're talking about using a volumetric pipette, it is incredibly precise. It's probably the most accurate piece of lab equipment that you're going to encounter in your labs. They are very expensive. So like an Erlenmeyer flask costs maybe $3 or $4 for a 250 milliliter Erlenmeyer flask. A 250 milliliter volumetric flask is going to set you back between $15 and $20. I lied. I think a 100 milliliter volumetric flask is about $20. So they're very expensive because of how precise they can be. So there are two kinds of volumetric glassware you're going to run into. There's volumetric pipettes, which is that kind of pipette. But like I said, it only draws up one specific volume. So if you want a 25 milliliter volumetric pipette, you can have that. You can also have a 10, a 5, and a 1. Okay. You can also have volumetric flasks. So volumetric flasks are the things that we will typically use to make our solutions when we are doing the labs, because we want to be kind of as precise as possible. This is what a volumetric pipette is going to look like. So they have kind of a long neck and a long bottom, and then they have this bulb in the middle there. And then at the top, they're going to have a line. Now, depending on the pipette you use, you're going to see a line that says TC or TD. TC means to contain, which means it contains exactly 10 milliliters. So if you fill it up to this line with the meniscus, it's going to contain exactly 10 milliliters. If you want to deliver 10 milliliters, which kind of, you think you'd probably want to do, you got to fill it up a little bit higher. And the reason for that is some of the liquid's going to stay stuck at the end of the pipette here, and that is going to be accounted for with the difference between the TC and the TD line. So when we're filling things up, a lot of times it just has the TD line and that's it. But once in a while, you'll see both of them, and you want to fill it up to the TD if you're using that to measure. A volumetric flask looks like this, and I believe most of you have used a volumetric flask at this point. Volumetric flasks come in any size all the way from 10 milliliters to 2 liters is the biggest one that I personally have in my room. They have a bulb at the bottom here, and then they have a line etched into the neck. And when you fill up your volumetric flask to get your precise volume, you're going to line your meniscus up with the line here to make sure that you have it perfectly filled. Okay. So if you are going to make a solution from a solid, what you need to do is you need to do some dimensional analysis. And I would say that people tend to really struggle with this, which is why we'll be going through some examples in the example video. You need to figure out how much of the solid you're going to need. So to do that mathematically, you need to first figure out how many moles of the solid you need to make that happen. And to figure out moles from molarity, and this is always, like, keep this locked away in your head. If you take the volume and the molarity as long as the volumes are in the same units, if you multiply those together, you always get moles. So M times V, molarity times volume, those always give you the moles of that thing you're looking for. And then once you get the moles of your solution, you can turn those into the grams and figure that out. Okay. Once you get to the point where you have your solution and the math figured out for how many grams, you need to go to a balance and weigh that out. And usually I recommend weighing it out on like a weigh boat. They use paper here, but use a weigh boat. And then what you're going to do is you're going to take those solid, however many grams you need, and you're going to put them into this volumetric flask. Sometimes it's hard to do that. And if your weigh boat doesn't like pinch very well, you're going to have to use a piece of, or you're going to have to kind of use a funnel to kind of help you make sure you don't, get your chemical kind of falling out of there. Some of your chemical will inevitably be stuck on your weigh boat. So what you're going to do then is you're going to hold your weigh boat and you're going to use a wash bottle to rinse the solid down into the volumetric flask. Then you're going to want to fill that volumetric flask up, I would say a little bit less than halfway, and you're going to want to dissolve that solid. You do not want to fill it all the way up and then try to dissolve it, because you need room for your solvent to move around your solute and get that dissolved. Then, like I said, you swirl it around. When it's all dissolved, you want to add water up to the line on the neck of your flask, and then you're going to close the flask. It's either going to have a stopper or some sort of cap, and then you're going to kind of invert your flask. So you'll flip it upside down, right side up, and you'll keep doing that until it looks consistent in its composition. And it will look different. When you flip that around, you will see swirls, because you will get a more dense layer at the bottom to start with where the chemical is. And then when you add water, you'll see the two layers intermingling with each other. Okay. Now, when you are making a solution from a solution that already exists, we call that a stock solution. So a stock solution is one that we just kind of have on hand that already exists. And usually what ends up happening is that the stock solution has a higher concentration that we need, and we're going to take that stock solution and add water to it to dilute it or cut down the concentration. So it's too high of a molarity, and we're going to take it down. The best example of this would be like our acids that we get from the chemical company come in like 12 and 18 molar concentrations, but we very rarely use that concentration. So then we'll take a little bit of the concentrated stuff and add water to it, and then you'll get a lower molarity. Okay. So what you need to do is you need to use the equation that's kind of shown here. It's M1 times V1 equals M2 times V2. And like I said in the previous calculation, if you take M times V, that'll give you the moles of chemical. So in this case, if I know I'm going to take a concentrated solution and make a less concentrated solution, I can figure out how many moles of the less concentrated, or the moles of stuff I need in the first place, and then use that to figure out my amount of either the volume or molarity that I need to make that solution. So again, the principle behind this is that the moles from my concentrated solution are equal to the moles of my less concentrated solution. So the way that this equation works is the M's in here are molarities, V's are the volumes. The volumes in this case can be in either milliliters or liters, regardless, as long as they are the same from start to finish. So it's got to be in milliliters for both or liters for both, and it works either way. And what you do is, depending on the problem, you are going to put your variables into here. And the big thing to remember is that it doesn't necessarily matter what the 1 and the 2s are, so a before or an after, but what you have to do is make sure that the molarity that you pick for the first molarity is the volume, or has the volume correctly joined with it. And I'll show you what that means when we get into the examples. But you're going to use this equation. And then what you do is you are going to use probably a pipette if possible. Volumetric pipette, maybe, otherwise just a serological pipette. And you're going to draw the liquid up into the pipette using a pipette filler, get the correct volume, and you're going to transfer it over into your volumetric flask. The beautiful thing about a volumetric flask is you don't ever have to worry about how much water to add. All you got to do is just add water up to the line. So you're going to pipette the liquid over. Then you are going to move it to the new flask. And then you are going to add water to that flask up to the neck and then invert it. There is one exception to that. If you are dealing with an acid, instead of having acid at the bottom and then adding water, what you're supposed to do is you put a little bit of water at the bottom of the flask. And the reason for that is that if you add liquid to a liquid, it is more likely that the bottom liquid is going to splash up at you when you add the new liquid. So you get some of it splashed back at you. And so if you have acid sitting at the bottom and you add water, you potentially could have acid splashing out of the flask back in your face, and that is not good. So what they do, it's a stupid phrase, but it's do as you oughta, put the acid in the water. So you got to put a little bit of water at the bottom, then you add the acid, and then you can start to dilute that. So that's just a little bit of a different scenario with that. There are two types of examples that we're going to work through. One of them is making a solution from a solid, and the other is going to be making a solution from a previously existing solution. So two problems I want you to try. The first one is going to be from a solid, and it's going to say, explain how you would make 750 milliliters of a 2.35 molar KOH solution, and I want you to include the mass of the KOH. So in this case, you're going to show me the math to prove it, and then you're going to walk me through the steps for how you're going to make that solution. The second calculations I want you to do, we're doing two different kinds because it's asking two different things. So if 45 milliliters of water are added to 250 milliliters of 0.75 molar K2SO4, what is the molarity of the new diluted solution going to be? And two, how much 2.8 molar HCl would be needed to be added to make 750 milliliters of a 1 molar solution? So I want you to do these as well. Give them a try, and then I will come back in the next video and then give you some examples. All right, good luck.